This is a presentation of the paper Video Summarization with Large Language Models. I'm a presenter, Minjong Lee. The goal of video summarization is to create a short version of a video that keeps only the important parts. We input a video through a summarizer and it gives each frame an important score. If we filter out less important frames, we can get a shorter video. There are three major challenges in video summarization. First, subjectivity of important score. What's considered important can differ from person to person. Second, the model needs to understand context. Without seeing what happens before and after, it might misjudge the scene. And third, video content is too diverse, which makes it difficult for a model to handle every video well. However, what if large language models evaluate the important scores of frames? LLMs can address subjectivity problem. They have strong background knowledge, so they can give scores that most people would probably agree with. Also, LLMs can understand context across frames. If we give LLMs multiple frames, they can consider what's really going on. And LLMs can handle diverse videos well because LLMs have been trained on large-scale datasets. So we came up with LLM vs our LLM-based video summarization model. Let me first give you a brief overview of our method. We propose the first LLM-based video summarization framework. MLLM captions each frame in the video, and the LLM scores its importance. Second, we adopt a local-to-global aggregation mechanism. This allows the model to integrate both local details and global context. Third, we leverage LLM embeddings. These embeddings provide rich semantic cues beyond generated text. This figure shows the overall architecture of LLM-VS. It's divided into three main steps. Let's start from the first step. To input a video into an LLM, we use multimodal LLM like Lava to generate a caption C. In step 2, the LLM scores local importance. We provide a prompt for scoring to the pre-trained LLM and then extract its embeddings. Let's take a look at how the prompt is structured. First, we group the caption C using local context modeling. To figure out how important each frame is, the LLM needs to see its surrounding context. So we group frames into a local window and ask how important is the middle one. For example, when window size is 3, we give captions for t-1, t, and t+1 to LLM, and the model scores the middle one of the local window. Then we slide the window through the whole video. After grouping the captions, we need to figure out how to structure the prompt to pass these captions to the LLM. So we designed the prompt using in-context learning with three parts. At the instruction part, we tell the model the description of frame scoring task, the expected output format, and the scoring criteria. Then we give a few examples. Examples are made using frame captions from the training set. Finally, in the query part, we add the local window frame captions of an input video. After providing the in-context learning prompt to the LLM, we extract the output embeddings from the LLM. These embeddings capture the comprehensive contextual information behind both the prompt and the answer. And we only use the query and answer embeddings, because what we really care about is how the LLM interprets the current caption and how it decides the importance score. The last step is global context aggregator. So far, the embeddings only reflect local context. Now, we want the model to capture the global context over time across the entire video. We input the query and answer embeddings, and the global context aggregator outputs an importance score S for each frame. We train global context aggregator with MSE loss. These are implementation details. For the dataset, we use the two most common datasets, SumMe and TVSum. For MLLM, we use Lava, and for LLM, we use Llama. We set the window size to 7. We use Kendall's tau and Spearman's rho for evaluation metrics. Let's compare with the state of the art now. The green box shows the LLM without fine-tuning. Even without fine-tuning, LLM performs competitively on the SumMe dataset. And LLM VS achieves state-of-the-art results on both benchmarks. Especially, LLM-VS outperforms existing multimodal models, which means our LLM-based approach is effective. We also check if the performance gains came from just fine-tuning on downstream tasks or from architectural improvements. First, we try using MLLM to directly score frames without captions. But when we pass captions to the LLM instead, the results are clearly better, showing that language really helps in summarization. Then we also check fine-tuning each model with LoRa, which gives clear improvements. But our LMVS outperforms everything, which means the performance gain comes not just from fine-tuning on downstream tasks, but from the design of our method itself. Now let's talk about different prompt types, how we ask the models to generate captions and scores. For the MLLM, we try two types of prompts. Center background type splits the image into center and background and asks for separate descriptions. And generic type asks for a detailed one-sentence description. We find that the generic prompt works better. For the LLM scoring, we also try two types of prompts. Texture explanation asks for a texture summary of the window, while the numerical evaluation style asks for a direct importance score for the center frame. Here too, direct scoring works better. Here's a qualitative result. The blue line is ground truth and the orange line is prediction. As you can see, the predicted scores align well with the overall trend in the ground truth. We also notice that action-related scenes tend to get higher scores from both human annotators and LLM-VS. To sum up, we propose LLM-VS on LLM-based video summarization model. If you're interested in more details, please check out our paper and project page.